Okay, guys, to pick up where we left off on Friday, now, I want you to notice something. If you see this particular diagram on a question, what particular diagram is this? This is a mass spec diagram. Remember what this is showing you. What does relative abundance mean? How often it appears. If I were to go outside and start digging stuff up, out of 100 of them, how many of them would I find in terms of relationship to their mass? Now, this particular mass spec was for the chlorine ion. Notice most of the highest percentage was found at what mass? At 35. Now, if you notice the rest of this, we talked about this. These three peaks way down here, what did they come from? The diatomics. Very good. That's why those peaks showed up. All right, so the last thing that I want to show you, we've covered all these other questions. Did we do C and D of this part? I don't think we did C. All right, let's look at C real quick. It says state why the spectrum of chlorine okay, let's tell you what. Let's do B. How many different isotopes exist for chlorine atoms? Do not say 5. How many different isotopes exist for the chlorine atoms? 2. What are the 2 isotopes? 35 and 37. Very good. So B is Cl35 and Cl37. So then, but you're going to say, wait a minute. Whoa. Why do you only have 2 listed and there are 5 total peaks? So that's going to be answered in the next question. C. State why the spectrum of chlorine consists of more peaks than your answer above. Where do those 3 peaks way down here, what do they represent? It's a different combination of each isotope to create diatomics. One more time. If you weren't here Friday, none of this is going to make sense. It's a different combination of the isotopes to create a diatomic. So, we said peak 3 was which 2 isotopes coming together? 2 35s. Because 35 plus 35 is equal to what? 70. It's equal to 70. Okay? What was peak 4 represented of? 35 and 37. Well, that's 35 plus 37 is 72. That's why that peak shows up. And then what was the last peak for? 2 37s. They got together to form a chlorine diatomic. So that's where that came from. So there's only 2 isotopes. You got to watch the video. It'll make way much more sense when you watch the video, I promise.
So shall I pay attention to this?
Yeah, you're going to have to know this. This is going to be on the test. Okay, so that's why if you want to know what this is on the exam, you're going to have to watch the video. I emailed it out, yes. Email me and I'll send it back to you. Okay? All right, so D, what do peaks 2 and 4 might be due to? Okay, very good. Is that right? No, it's 2 and 4. Peaks 2 and peaks 4. All right, peak 2, this is what I want you to write for part D. Peak 2 is the Cl37 isotope. Cl37 isotope. Peak 2 is Cl37. And what is peak 4? Very good. It's going to be the Cl. Come on, pen. Come on, pen. Cl35 and or plus a Cl37. All right, Jordan, see if this makes sense. Okay, I have a ping pong ball and a golf ball. Do they weigh 2 different things? Okay, pretend for just a second they're the same. Okay, ping pong ball, golf ball. This big peak would be the one that weighs the least. Okay, so if I went out there, I would find more ping pong balls. Yes. Okay. This peak represents the heavier object, which would be the golf ball. Okay. What is a diatomic molecule? When 2 of the same things stick together. Okay, so we're going to pretend we're going to stick a ping pong ball and a golf ball together. You with me? Okay. This one would be the 2 ping pong balls stuck together. So it'd be 235 stuck together because 35 plus 35 is 70. Okay. This peak would be the ping pong ball plus the golf ball stuck together. And then the last peak would be 2 golf balls stuck together because they're the 2 heaviest. Because 37 plus 37 is 74. Does that help? Exactly, because it's just these 2, and you're just sticking them together in different fashions. Yes, sir.
So 37 is on the 1 and 2.
Yes, that's just CL37 by itself. That's just the golf ball.
And so there's more with 37 plus 35 than there is just 37.
Yes. Here's why. That's you brought up a great point. So what he just said is there are more 35 37s than there are just 37s alone. Why is that true? When we see chlorine in nature, how do we see it most often? By itself or as a diatomic? As a diatomic. That's why. Now, why is 5 so small? The reason 5 is so small is because 37 is very rare. So to have automatically, for some reason, 2 of them to happen to stick together, very, very small chance of that happening. Okay? So that, very good question. That's how you think analytically through that stuff. Okay? All right, so here's what I want you to do. Number 2. Yes, sir.
Again, the 35 and the 37 represents the, what does it represent?
That's the mass of the atom.
The atomic mass.
The atomic mass of the atom. Okay? All right, so here's what I want you to do. I want you to actually practice calculating this. Now, do you agree? Question 2. The mass spectrum of the sample of chromium shows 4 peaks. Here's the peaks. It's going to show a peak at 50, at 52, at 53, and 54. Use the data below to calculate the relative atomic mass for chromium in the sample. If I needed the mass of chromium, could I not look on this? But here's what's going to happen to you on test day. You know what chromium is going to turn into? Element X. And you're not going to have any clue what it is. So you're not going to be able to look at this and say, oh, that's it. So you need to know how to calculate it. So this is, if you don't remember the formula, this is the formula. Okay. First of all, which isotope is present in the most abundance? 52. I'm just going to go ahead and tell you this. The mass of chromium on the periodic table, according to the AP exam, is exactly 52.00. Exactly. But this is the math that they want us to figure out. I'm going to forewarn you, it's not going to be exactly 52, but that's okay. You just want to see the process that it comes around. So here's how you calculate it. It's the mass times the percent abundance of, let's call this number 1, plus the same thing of the percent abundance of number 2. Does that make sense of what I'm saying? So it's the mass times the percent plus this one, plus this one, plus this one. You with me? Do you agree that this is the mass and the percent abundance for the first one? Calculate that. And then calculate this one and add it to the first one. Y'all looking at me like I'm crazy. Does that make sense? Okay. All right, let's try this. All right, so mass, 50 times, is percent a real number? No. What do you even need to change that to? 0.043. All right, so that's for the first one. Plus the mass, the second one is 52. What's the real number for percent there? 0.838, right? Okay, plus, you see what I'm doing now? It's the mass times the percentage. Go ahead and finish that out. Yeah, go ahead and get one. Say that again. You're looking for the mass of chromium, the relative mass of chromium. Jordan, here's the deal. All of these numbers on this periodic table are the relative masses. Okay? The reason we have these numbers on the periodic table come from this experiment. So let's pretend that we find some brand new element we've never found before, and we want to know the average atomic mass of all of its isotopes. This is the math that you'll have to do to determine it. Exactly. Okay. It is an average abundance, but it's the mass of their abundances, if that makes sense. Okay. So to finish this out, it's going to be 53 times 0.095 plus 54 times 0.024. Has anybody actually done the math on this? Okay, what is it? 52.057. So 52.06. That about right? Okay. Everybody agree? So that's what you come up with. I'm going to give you a hint, hint, wink, wink. You may want to listen to this. Hint, hint, wink, wink. You may want to listen to this. Let's pretend all of a sudden they give you all of this in blue except for one part. And they give you what's in red. What if they want to know, I'm just going to pretend, let me color this white. They want to know what the percent of that particular isotope is. Do you agree that I would plug in X for right there? Okay. You already have 52.06. If they want to know a percent, could you turn that into an algebra problem and figure out what the answer is? Okay. Do you agree that you would multiply that? You do all that together, right? Do all that together and then subtract it from this number? Yes? Yeah. Okay, combine like terms and then solve for X. Yes? Okay, you know how to do basic algebra. Hint, hint, wink, wink. You may need to know how to solve for a percentage. What do you mean turn them into percentages? Yeah. All right, well, let's pretend that that's not that kind of question, but you're still going to have to find a percent. How about that? You're going to have to know a percentage. Yeah, it can come from 100. Just go with me. Okay. Just go with me. Okay. All right, now, here's what I want you to do. Draw a sketch of a spectrum that will be produced from the data above. Just try to draw a sketch.
I don't know. What do you mean by that?
All right, draw a sketch of the spectrum. This is a spectrum. Try to recreate. All you have to do is draw an XY coordinate. Just add a page below. Just draw it on the page below. Just draw an XY coordinate. Guys, in this class, labeling coordinates will make you or break you. It will give you a point or will take your point away. Okay? Label your coordinates and draw the peaks relative to the percentage sizes. Is it going to be perfect? No. That's why it says sketch. Yes, ma'am. Yes, absolutely. Okay, go ahead. Okay. State why the spectrum of chlorine consists of more peaks than your answer above. Do you agree that in B we got two? We have two. The only two isotopes, because the question is how many different isotopes? The isotope was 35, 37. The question of why does it contain more peaks? So we've already established that these are our 35 and 37 peaks. So how in the world did these three show up? This is chlorine atom. Chlorine can exist as a diatomic, and so it's a different combination of the isotopes to form a diatomic molecule. Number 2 represents the chlorine 37 atom. You with me? And then peak 4 represents a diatomic 35 and 37 coming together.
So 2 represents the
just the 37 atom itself. It's me handing you one golf ball. Okay? Hopefully, your sketch should look something similar to that. No, it'll be every test you will ever take will all be on pencil and paper. Okay. Now, let me ask you something in terms of relative size. Do you agree that it's hard to make 83.8% real close to 2.4% in a graph this small? It's hard to do that. That's why it's a sketch. But do you agree that it's much easier to make 4.3, 9.5, and 2.4 relative sizes? How could you make them all relative? And what do I mean by relative? Closely related?
Yeah.
Your cousin is your relative? Aren't you closely related? Do you agree that 4.3 is about double 2.4? So your line for 4.3 should be almost double 2.4. Does that make sense? And then how much more is 9.5 than 4.3? It's about double again, right? So your 9 should be about double the 4. AK, you with me at all? You're looking at me like I'm crazy. AK, do you agree that 4 is almost double 2? Do you agree that 9 is almost double 4? So when you go from 2 to 4, the line should double. When you go from 4 to 9, it should double again. Does that help? Okay. So again, it's relative. So in that case, how much larger should 9 be than 2? Not 3. 4 times as big. Because you doubled and doubled again. So it's quadruple the size. And it's relative. Now the 83 just jacked that sucker up through the roof and try to get it as close as possible. All right, the last thing that I want you to make note of. Okay? The path below shows the magnesium 25 ion through a mass spectrometer. Okay? Do you agree that this down here, I'm just going to circle it, this is the electron flow? What are the electrons doing to those atoms? Very good. Charges it. It charges the atom. What is this big gray looking thing?
That's your catalyst.
Not catalyst. It's the magnetic field. Very good. What is that magnetic field going to do to that charged atom? What's it going to do to it? It's going to bend it. Okay? This is a quiz for you. I need you to label 2 parts. Down here at part D, this is like the reader, the recorder, the receptor. I want you to label. One's going to go on top and one's going to go on bottom. Label where the heavier and the lighter atoms would show up. Label basically both ends of these lines. One's going to say heavier, one's going to say lighter. Pick which end the lighter and heavier would go on. Don't say it out loud. Think about the shape of the tube. Think about the magnetic field and what would happen based on their masses. Which part? Oh, it's already, yeah. Is it already on there? Aw.
Well, something's
You kind of have to read through it.
but it's not lightweight.
All I'm asking for is lighter and heavier. You should be able to figure that out based on the curvature of the device. How many of you put the heavier is on top? Very good, Alex. You're right.
Yeah.
Tanabe, guys, yeah, very good. This is the heavier.
No, I'm not.
Guys, when I say it, you're gonna be like, oh, I get that.
We talked about it already.
We have talked about it.
I knew I was right.
It's basically that. All right, this right here is what we call the reader, the receptacle. All right, the atoms are going to come flying through here, and this is going to be the heavier atom, and it's going to hit right there. Okay, the lighter atoms. Let's change that to orange. All right, the lighter atoms are going to come through, and they're going to bend, and they're going to snap down here, and they're going to hit at the bottom. Okay, that's kind of what happens. Why do the heavier atoms hit at the top and not hit at the bottom?
They're not as affected enough.
If me and Alex run into each other or me and Matt run into each other, which person will be more affected by the force? Alex. Why Alex? Well, he does have a scooter because he's lighter. So when you send that light particle through that magnetic field, what's that magnetic field going to do to that light particle? It's going to snatch it down. If it's too light, physically, does that make sense? If it's too light, what's going to happen to it? It won't even make it. It's going to slam into the wall right here. If it's too heavy, will it affect it enough to bend it? Nope. If it's too heavy, it's going to be cruising along, and it's just going to slam into the wall right there, and it will never make it. So if it's too heavy, it won't bend it. If it's too light, it bends it too much. Yes, sir.
Say if that tube is flipped upside down.
It would the parts would flip. Yep. You just have to think, which particle is the magnet going to affect the most? The farther the bend, the lighter one's going to go, the more the bend. Okay? All right, so hopefully that makes sense. Again, watch the video. If you were here Friday, a lot of that should make sense for you. Okay? All right, let's flip gears and let's go over to a hydrate. The first thing I'm going to ask you is, what is a hydrate? You guys can read. Good job. Now stop reading and tell me what it is. Or continue to read. Physically, what does it mean? All right, let's just pretend for... All right, so let's just pretend for just a second that I've got... What compound is that? Copper what? Copper 2 chloride. If I wanted to hydrate this particular... Do you agree this is a molecule? If I wanted to hydrate it, do you all agree that I'm going to have to add some water to it? Now, here's the issue. Guys, y'all listen. This compound has been hydrated. It's added water molecules to it. Does it change its properties? Say yes. Yes, it changes its properties. Does it also affect its mass? Say yes. Yes. Okay. In the winter, do you weigh more than you do in the summer? Yeah, because you have on more clothes. Right? Okay. And you eat a lot more. It gets Thanksgiving, it gets Christmas. We all get fat and lazy because we can't go outside. Okay, it happens. So here's what's happening. Please, guys, y'all listen. So a hydrate is a compound that has water attached to it. Now let's think for just a second. If I wanted to do a lab, and the lab I wanted to perform, I only needed the copper 2 chloride. Would the water affect this lab? Yes. So in essence, do you agree that I'm going to have to get rid of this water? Physically, in a lab, how could you make that happen? Heat it up. When you add heat, guys, that should make sense. When you add heat, what does it make the water do? It is fire. It's going to break these bonds, and you're going to turn that water, and you're going to get rid of it. You're going to basically, essentially boil it off. So once you have removed all the water, what do you have left? The compound. That's what you're going to have left. All right, so let's go back and let's read now. Let's talk about what it is now that you've seen a visual diagram. All right, so highlighter time. A hydrate is an ionic compound that contains water in its structure. A hydrate, why is it very important that it says an ionic compound? Because a hydrate does not exist with covalent or molecular molecules. Okay, it's only ionic compounds. So here's what we're going to do. To determine the formula of a hydrate experimentally, here's the important thing. Highlighter, change your color. Calculate the mole-to-mole ratio of the water to the anhydrate. Can you compare things just using grams? No. You must always compare them how? Mole to. So what they're asking you to do is to calculate the mole-to-mole of the water portion. What do we call, and this is where an arrow is going to come into play. What is the water portion called? Please draw a line over to the hydrate. And then it says compare the hydrate to the anhydrate. What in the world is an anhydrate? Don't read. Tell me. No. That's a good thought, but no. Okay. When you're in English class and you add the prefix "an" to something, what does that mean phonetically? Not or without. Very good. So an anhydrate is without water. Okay, fantastic. So here it is, the anhydrate. The anhydrate is the substance that remains after the water is removed. Okay? The anhydrate is the substance that remains after the water is removed. So in this particular example, what is the anhydrate? I'll go right back, Matt. Copper 2 chloride. If I tell you that I start with exactly 5 grams, now listen how I say this, of the hydrated molecule. Do you agree that's with the water? Okay. After what is this? After I heat it up, I'm only left with 3.2 grams. I'm throwing these numbers at you. So, one more time. I started with 5 grams of the compound with the water attached. I heated it up, and after I heated it up, only 3.2 grams remained. Why did the mass go down? The water was driven off. Can you tell how much water exactly was driven off? Very good. Look at you. You knowing what you're doing. Just a simple subtraction. I mean, it could be like stubby fingers, but that would be weird. Okay? So, the way you determine the amount of water is simply by subtracting. Now, let's go back for 1 second. Remember, please listen, guys. These 2 units that we're working with in this are grams. Can you compare grams? We've already said, what are you comparing? Mole to mole. Could you easily get these into moles? Yes. All right. So now let's look at one more thing. Okay. When a hydrate is heated, the water molecules are driven off as steam, leaving behind the water-free anhydrate. That's exactly what we just said. All right. The first step to finding the formula of the hydrate is to record the mass of the hydrate. Why do you need that? Why do you need the mass of the whole thing with water? Bingo. So, sorry, that's not what I want. I'll tell you what, yeah, we can do that. Change your color. All right. First step, mass of the hydrate. That's the first step you're going to need. Now, this particular worksheet doesn't say it, but there's actually another thing that has nothing to do with the compounds and the heating them up, but it's very crucial to the lab itself. What else do you need the mass of? Think about lab. It's the specific lab. Okay? If you have copper 2 chloride in your hand, are you going to heat it up in your hand? No. What are you going to heat it up in? The mass of the container. Very good. So somehow, matter of fact, you can add it like right here. And the container. Please add that. Now last year, I think my class, I know we did this. We did the magnesium oxide where y'all had to use the crucible. These labs are performed using a crucible. Okay, I know you're like, that's a book. It's a chemistry tool.
What's the crucible?
I'll show you in a minute. Okay. So again, why do you need the mass of the crucible? Because after you heat it up, are you going to pour that stuff out on the scale and then pour it back in? No. So you're going to have to be able to subtract that from it. Okay? So number 2, after heating the hydrate, the mass is determined for the anhydrate that remains. The mass of the water present is calculated by, so this is what I want you to highlight. Okay? Mass of the water present calculated by finding the difference between the mass of the hydrate and the mass of the anhydrate. You've already seen that. I've already showed you that. You yelled at me the answer everybody did, and you knew what it was. And here's again, this is restating a fact we've already stated earlier. Once you have the masses, change color, what do you have to do with those masses? The masses are converted to moles. Okay, so let's look at a particular example. Can I clear all the highlighting? So here we go. The mass of the hydrate. What is the ionic compound the hydrate is with? What is that? Calcium chloride. And then you have a little dot, and then you have an X, and you have a water. What does that X represent? Any number. The number of waters specifically. We're going to have to find that X. Okay? So this is how much you start with, right? You start with 4.72 grams. The mass of the anhydrate. This is what the point what I want to make. What does the anhydrate mean? No H2O. So how can you determine the mass of water that was kicked out? So minus, and it's going to give you that value. So we started with 4.72 grams. We heated it up. We had 3.65 grams left, which means of the original 4.72, 1.18 was water. Yes, sir.
Why is it 4.74, but like all of it together is 4.72 on top?
What do you mean?
Isn't 3.56 plus 1.18?
Is that math wrong? Or that math wrong? It dang sure is wrong. Wow. That's embarrassing. It actually should be 1.16, shouldn't it? Wow, that's sad. Yeah, do me a favor. Change that. Did I look like I create this worksheet?
Yes.
Thanks for giving me that much credit, but I didn't. Wow, that's pretty embarrassing. Right now it's in grams. You got to change it to moles. Yep. All right, so let's look at the math that they did. And all of this is going to make sense. Because the rest of it makes sense, I promise. All right. So we know to find the mass of the water, we're just going to do basic subtraction. We're going to convert the mass of the anhydrate to the mole. Do you agree that we're starting with grams of calcium chloride and we convert it to moles of calcium chloride? Every single one of you can do that. The next step, we're going to take the grams of water and we're going to convert the grams of water to what? And this is the new step. This is the last but easiest step. It's new. It's the only new thing we're going to talk about. And this is what I want you to write down. What do I mean by ANHY? Anhydrate. This is what you do. You take the moles of the water that you just found and you divide it by the moles of the anhydrate, and it's going to give you a number. That number should be a whole number, and that's your number of what? Nope, that's your number of waters. Moles of ANHY. I just didn't have enough space. It's anhydrate. The only new thing that you've seen, the first part is a basic subtraction. The second part is a conversion from gram to moles. And the last part is a simple division. Let me ask you this. I told you that this number should be a whole number. If for some reason you accidentally flip these over, what would your number look like? A decimal. Did you do it right if you got a decimal? It's just like the empirical molecular formula stuff. Okay? So, I want to work problem number 1. All right, a hydrate of magnesium sulfate has a mass of 13.52 grams. This sample is heated until no water remains. The MgSO4 anhydrate has a mass of 6.60. How do we know how much water was present? Subtract. All right, so this is what I want you to do. Okay? So, it's the hydrate minus the anhydrate. I know the anhydrate was 6.60 grams. What was it? Was 13 point something. 52. Thank you. Okay. Now, these are both grams. All right. So we're going to get 2. We're going to get 9. 12. We're going to get 6.92 grams. And we're going to get water. Simple, right? What's wrong?
Shouldn't the anhydrate be on top because you're subtracting the hydrate from the anhydrate?
No. The hydrate is the highest mass because it's got the water attached to it. Look at the question. It says the sample is heated. The anhydrate has a mass of. If you flip it over, you're going to get a negative number. You can't have a negative mass. Okay. Does that make sense?
Yes.
Okay. All right. Now we're in grams. What do we need to do next? Convert it to moles. Very good. All right, so 6.60 grams. And this is, real quick, what is the formula for magnesium sulfate? Because that's important. Very good, MgSO4. Give me just a second, and I will look up the molar mass. Y'all go ahead and do the water, because you should know the molar mass of water, shouldn't you? 18.02. Give me just 1 second, and I'll do the magnesium sulfate for you. All right, 16 times 4 plus 32.06 plus 24.31. It's 120.37. Which gives me 0.0548 moles. And the water is 0.384 moles. Okay? All right, so that's what I did. I did basic subtraction. I converted grams to moles. I divided the moles of water by the moles of the anhydrate and got the number 7. The last thing I'm going to ask, is that your final, complete, correct answer? No. The final answer they wanted was the formula. The formula. So what would the formula be? Now, we have another name for this thing. Instead of calling it a hydrate, sometimes you'll hear it called a dot water. Do you see why it's called a dot water? It's a dot, and how many waters you have?
Dot water. 7. You have 7 waters.
There are 7 waters. The formula is the answer. Just like the empirical formula, you know, whenever you get to like 1, 3, and 7, the answer has to be the whole formula. Yes.